Good evening, everybody, and welcome to the April meeting of the Astronomical Society of Glasgow. Unfortunately, David can't be here because he's had a family bereavement, and so the first thing I'm going to do is read out the Secretary's announcements, and if there's stuff that you know about that I've missed, just call in, okay? The next event that will be happening will be on the 25th of April, when there will be a meeting of the imaging group, which will be on Zoom. I don't have a time for that yet, but no doubt that they'll put that out. The next meeting of the beginners group will be at Acre Road on May. No, is it Zoom? Sorry. It's what? So it's Zoom. Right, okay, so right. So the next meeting of the beginners group will be on Zoom on May the 10th. What time's that? How long is that?
Starting at 7:30.
7:30, okay. And the next observing group meeting on Zoom, which I will be doing on Sunday the 12th of May at 7:30 p.m, when we'll discuss what you can see in the May sky, and also a chance for people to talk about what observing and what they are being doing. There is a meeting of the British Astronomical Association on Saturday the 11th of May. I think it is. It's in Greenock. Something like the sound of the stars. There is a charge. I think it's £11. If you're a member, I think you get a discount. But if you're interested in going to that, you could maybe Google that. So that's basically the announcements. Which then leads me on to the main part of this evening. And it's a pleasure to have Dr. Benjamin Bose, if I pronounced that right. He's from I'm very old-fashioned, so I always call it the Royal Observatory, Edinburgh, ROE. Is it UK Science and Technology?
Oh, people still say ROE.
Yeah, it's the Royal Observatory, Edinburgh. So, and he's going to be giving us a talk about the disappearing, discerning a darkening universe. Okay, so pass it over.
Thanks very much. Hi everyone. Hi. So first of all, thanks very much for the invitation. It's great to be down here and given the opportunity to talk to you a bit about what I do at the Royal Observatory. I'm a theoretical cosmologist, so I'm a bit far from the observational side. So this talk was really good because I got to go into the history of cosmology, but also the observational side of cosmology, which was really nice. So as was said, my talk is about the darkening universe and how we know that it's darkening, what that actually means, and how we can learn more about the universe from the very fact that it is darkening. So I've split the talk a bit ambitiously into 3 parts. So the first is pretty long. It's 4,000 years of cosmology, but it won't take 4,000 years, hopefully. The second, we'll move on to the biggest problem in physics, which is something that I work on. It's more of a theoretical problem, but it's based in observations. So hopefully there'll be something interesting for everyone there. And finally, I'll move on to what work is actually going on at the Royal Observatory related to this biggest problem in physics, but also, of course, related to cosmology. So spoiler, the biggest problem in physics is actually a cosmological problem. Okay, so let's start with 4,000 years of cosmology. So I looked at the definition of cosmology. And so it says the science of the origin and development of the universe. But I thought that cosmology was being practiced, ancient Greece, people were doing cosmology. And I understood then that there were 3 different words. So there's cosmology, there's cosmogony, and there's cosmography, I think. And the latter two don't have this word, basically. So they don't apply the scientific method to understanding the universe. But it did start with cosmogony, and that had more of a, let's say, a mythological approach. It wasn't based in, hypothesis, observe something, and then refine your hypothesis. It was really based on what people saw and the ideas that they had about what they saw. So let's take a look at some of the cosmological models. So I'll just use cosmology from now on. The cosmological models of the past. So we can go back 4,000 years, a bit more, to Babylonian society. And they thought the world was divided into two. So you can see at the center of this sphere, you have two pyramids. There's the pyramid of the living and there's the pyramid of the dead right below it. And it's separated by a fluid, which is very similar to an ocean. And then you have these spheres around where the gods would live. So this is how they thought the universe was. You move forward, you have a Hindu cosmology, where you have the manifestation of the universe and the destruction of the universe occurring with every day that this god lived. And this god would live for 100 years. So 100 years times 365 days is how many times the universe would go through this cycle of being born and destroyed. And every time it was born, it would be manifest for about 4 billion years, they thought. But then they had the cycle in the cycle, so there was a higher god, and that god also birthed the mini gods, and so many, many billion years in these infinite cycles of the gods' lives, as you can see here. And moving forward, so ancient Greece, we had Anaximander, who thought that there could be a multitude of universes out there. There didn't just need to be one, but you also had Muslim polymaths thinking about the universe too, like Fahd al-Rakim in 1149 AD, who also thought that there could be many different universes. And notably, I always forget his second name, but Robert Gossechter, I think he was a mathematician, in 1200 AD, who thought that the universe was born from a big burst of light, which is very reminiscent to a theory we're going to be learning about in just a bit. But he also thought that there could be many different universes. And finally, we have, maybe something that many more people are familiar with is the Catholic cosmology, where we have heaven and earth, and there are the gods who live in heaven, and us mortals who live on earth. And there you have a picture from Dante's Inferno, where you have Beatrice leading Dante through heaven. So this is heaven. Okay, so that's 4,000 years of cosmology. I want to move on to the actual definition of cosmology, which includes the word science in that. And to introduce science, we're going to do a little exercise in applying the scientific method. So for this exercise, we'll take two different theories of the Earth. So we have the round Earth model, and we're going to compare that to the flat Earth model. So the scientific method approaches this problem by taking a bunch of observations. You have a hypothesis, you observe things, and you see how many things are consistent with your hypothesis. If some things are not consistent, you try to refine, or you choose a new hypothesis. So we'll try to apply these two hypotheses to the real world. So let's look at the flat Earth model to start. So the flat Earth model says the Earth is flat. So that can explain quite a few observations. Why the horizon looks flat, that's very consistent with the flat Earth model. Why is the water level flat? That's great. Yeah, it explains that too. Why are Newton, Galileo, and Neil Armstrong all Freemasons? It also explains that. And I remember an instance about a year ago where I was in a bar and someone was trying to explain to me why the flat Earth model works well. And he looked a bit like, the guy who will come up soon. But let's look at the things that you can't. So why are there eclipses? It does very poorly with explaining things like a solar or lunar eclipse, so it doesn't do well there. The motions of the planets, you'll need to refine the flat Earth model a lot to get the motions of the planets. First of all, what are the other planets? I'm not really sure. What is gravity? So it doesn't really explain why we are stuck to this flat Earth. What is the force there? Why are there flights from Japan to USA? I can't explain that. And actually another anecdote with that, my cousin called me up when I was in my PhD, and she said, I saw a video on YouTube about the flat Earth. And she's like, can you explain to me why we think the Earth is round, and how we can be sure about that? And I told her, okay, so you have a friend in Japan, give them a call, and if they say it's nighttime, that means the Earth is round. And so that's, if you're ever confronted with a flat earther, you can tell them to call a friend on the other side of the globe and see if it's daylight or not. And hopefully that will convince them, probably not. Okay. Why are there time zones? So it's very related to the anecdote I just told you. Why do ships sink over the horizon? Okay, so it doesn't do very well. And of course, if you get, well, I don't know if any of you know that, I'm American, I know this guy very well. But he's a well-known conspiracy theorist in the States, Alex Jones. And so, of course, if you bring him all these things that are inconsistent with whatever conspiracy he's promoting, he'll give you a model which explains them all. Because you can always make your model infinitely complicated to explain whatever you see around you. The problem is that if you have a working flat Earth model, you have to introduce so many degrees of freedom. It has to be so complex to explain everything that you see. Let's look at the round Earth model. In particular, we'll look at a theory which does really well in this round Earth context. So, I don't know how many of you can guess who that is. That's Isaac Newton. And in 1687, he came up with his famous law of motion. So he says, the motion of a body is proportional to the mass that is attracting it. And so by just applying that law to a round Earth system, you can get all the phenomena that we saw before. We'll go through them in a bit. But like I said, mass is proportional to motion. The bigger the mass, the more motion it causes other bodies to undergo. So here we see the sun is very massive. It's causing a big motion of the Earth. But the Earth is very small, not very massive, so it causes a very little pull on the sun. So the sun does move because the Earth is there, but it's negligible. Okay. So let's look back at our different observations and see what the round Earth model can do. Okay. So why is the horizon flat? It can definitely do that. The Earth is very big, so if we are sitting at the spot on the Earth, it will look flat locally to us. That's fine. Why is the water level flat? Well, like I said, Newton's law, it pulls everything towards the center of the Earth. The Earth is very massive, so the water level will look flat. It can't explain this one, unfortunately, but we'll move on. Let's see what it can explain on the other side. It can explain eclipses. We have the round Earth moving around the round sun, and it sometimes covers the moon. The moon sometimes covers the sun, and sometimes the Earth covers the moon. So we can explain eclipses. It can explain the motions of planets very well. It can explain why things fall to the ground. It can explain why there are flights from Japan to the USA, etc., and it does extremely well. But then, obviously, if you're talking to a conspiracy theorist, they'll always come back and say, well, what about Newton, Galileo, and Neil Armstrong? Okay. So why did we do this exercise? So we did this exercise because reality constrains us. It constrains all the ideas that we might have about it, and it narrows that very large set of ideas to something, to a very, very small subset, depending on how many observations you look at. And as scientists, this is exactly what we do. So we'll be revisiting this idea many times during the talk. We look at observations, we compare them to our hypothesis, and we construct credences or probabilities of our hypothesis being true or not. And so in this case, we have the round Earth, we have the flat Earth, and I hope I've convinced you that the probability of us living on a round sphere amongst other round spheres in space is quite high. Okay. Of course, we can't rule out the flat Earth. That's why I didn't assign it 0 probability, but it's very unlikely. Okay. So, as time progressed, we found that Newton's theory couldn't explain everything that we observe. So like I said, you bring in more observations, your hypothesis starts to feel the need to be refined. You need to dig a bit deeper and find new ideas to explain these new observations. So one of the things Newton couldn't explain was how Mercury's orbit shifts around the Sun. Specifically, we call it the perihelion, and the perihelion shifts with every orbit. It's basically the point where it's closest to the Sun. And that shifts. And Newton's theory couldn't really explain the exact motion of this perihelion. There was also the bending of light. So Newton's theory cannot explain fully why we see things like this. And this is an image of a galaxy. So the blue arc is a galaxy very far away, whose light is being bent by a near galaxy. So the red point in the middle is a nearby galaxy. So Newton's theory cannot explain things that we see in the night sky like that. And Newton's theory, if we just accepted Newton's theory, we wouldn't be able to use things like Google Maps. And I'll explain in a bit why that's true. Okay. So what happened? We had these observations, Newton's theory wasn't consistent with them. We needed something new to explain all the things that we were seeing. And so in 1915, another very famous scientist came along, so this Albert there, and he came up with a new relationship between motion and mass. And so basically he added an extra step. So he said energy, and you know Einstein's very famous equation, E equals mc squared, you have an equivalence between energy and mass. So energy causes curvature. And curvature of what, you're going to ask? Well, curvature of space and time. You know, when I was doing my bachelor and my master's, I would always hear Einstein says mass causes space and time to curve. And what does that actually mean? So basically what that means is that you're in different points in space, and you are perhaps close to the Sun, as you're seeing here. There's a lot of curvature. That will cause you to make measurements which are different when you measure space, when you measure time. So for example, my watch, or I have a ruler, those will change depending on how close to the Sun that I am. If I'm far away from the Sun, the time that I measure on my watch, the length of my ruler will change to an observer, let's say, very, very far away. So space and time become malleable, and the degree to which they're shifted around depends on the energy content of that space. Okay, but then how does that relate to motion? Well, basically everything in the universe follows straight lines, and if you generalize a straight line to a curved space-time, you get motion, which we observe. Basically, things fall into the Sun, things move around the Sun. Like I said, we have light bending. That is really just following a straight path, but in a curved space-time. So let's take a look at these things. It could explain Mercury's orbit extremely well. So check there. It could also explain, like I said, the motion of light around massive objects. So it could explain things like this. Like I said, photons, well, particles of light, they move in straight lines, curved background. That means the trajectory of these light particles is going to shift. And so that's why we can see light being bent around massive objects. And like I said, if you're close or far away from an object, it changes the time that you measure or the distance. And GPS is extremely precise. So, you know, Google Maps can tell me within 5 meters where I am on the globe. And to get measurements that precisely, you need to account for the shifts in the measurement of time of the satellite being far from Earth and we being on the surface. If you don't account for that, you'll get very, very, very big errors on where you are using GPS. So thanks to Newton's theory, we can explain all these observations and we can have things like Google Maps. So it was extremely successful, and Einstein was extremely pleased with himself, with his new theory of space-time and curvature. And so I think I was quite happy I found this photo of him on the beach, chilling after he came up with this amazing theory of gravity, but also of the universe. And so in particular, Einstein's idea of the universe was that it was static, it was a constant, it wasn't evolving, the universe wasn't evolving, and you had a fixed amount of matter within the universe. And that was his idea, and it was well accepted at the time because there were really no observations to go against this idea. And he had a lot of observational support from things like I told you, like the shift in Mercury's orbit. So that was in 1917. 10 years later, well actually a bit before, there was Friedman before, but we'll talk about this guy. So in 1927, there was a guy called Georges Lemaitre, who was a Belgian priest. And he came up with a slightly different idea of cosmology. So there's George on the same beach as Einstein explaining to a woman his theory of the universe. I don't know what he's explaining to her actually. There probably something, well, he's a priest. So his idea was that the universe was not static, but that it was expanding. So, like you saw there, started from a point basically, and space and time expand outwards, and you have this dynamic nature of space-time. And it was actually Georges Lemaitre who first coined this idea of the primeval atom, or the point where all space-time began. So George's cosmology and Einstein's cosmology were at odds. Einstein wanted the static universe, George wanted the expanding dynamic universe. So what do you do when you have two theories which are competing? You need more observations. All right. So let's take a look at more observations. So 2 years actually after Georges Lemaitre proposed his dynamic universe, there was an unexpected observational result, which I'm pretty sure, well, some of you definitely know about this result. So in 1929, 3 people combined efforts to produce a very interesting relationship. And I'll explain that in a bit. Here we have Edwin Hubble on the left, we have Henrietta Leavitt in the middle, and Vesco Slipher on the right. They all contributed to this observation in a very big way. So what was this observation? So here we are on Earth, and what they were doing is they were observing nearby galaxies. So they observed the galaxy, and they also measured the speed at which it was moving. So they observed this nearby galaxy, they measured the speed, and they found that this galaxy was moving away from us at some speed. They moved on to observe a galaxy a bit further away, and they also measured its speed, and they found that this galaxy was also moving away from us at a slightly higher velocity. And they repeated this for other galaxies which were even further away, and I guess you've caught the trend by now. These galaxies were also moving away from us, and the further away they were, the faster they were moving. And so they came up with this really nice relationship, where on the y-axis, so the vertical line, you have the speed of the galaxy away from us, and on the x-axis, the horizontal line, you have the distance of that galaxy from Earth. So you can see that there's this very nice relationship. As you move further away from Earth, the faster the galaxy is receding from us. Okay, so what do we make of this observation? Very strange. We can come up with some hypotheses. So the first is galaxies don't like us, and they like us less the further they are from us. You could say that. Or the universe and space in particular are expanding. So if space is expanding uniformly in this room, there's more space between me and the people at the back seat. So that means, hey, that means you are going to move away much, much faster than, say, me and Bob. So Bob will be moving away much slower because there's less space between us. So as soon as you make space dynamic in that sense, you explain this observation. And so remember, as scientists, we want to adapt our credences in certain hypotheses based on observations. So we have to accept that space is expanding if we want to believe these observations. And I encourage you to think of other explanations for this observation, which are perhaps simpler than the one that is proposed here on the right. Okay, so good. We have more observations. We have Einstein and George. And unfortunately for Einstein, George's cosmology of this expanding universe wins out when we look at the observations of Hubble, Henrietta, and Bose. And so I found this really nice quote from George, which really encapsulates what we're trying to do, is that progress is the discovery of a more and more comprehensive simplicity. So what we try to do as scientists is we try to explain as many observations as possible with as few parameters or as few knobs as possible. And if you remember, the flat Earth working model had many, many different knobs, very complex, not very attractive, whereas this model of cosmology is very simple and it explains most observations. So let's take a look at what this looks like visually. So what does an expanding universe look like? We have a bunch of galaxies here. Some are very far away from Earth. And I'm going to click, and these galaxies are going to move away based on how much space there is between us and that galaxy. And so this is exactly what it would look like. And you can see as we move forward in the future, things get quite dark. So now you're starting to see why the universe is darkening. But if we reverse time, what happens? Because we're also interested in the past, in cosmology. We want to know everything about the universe, its past and its future. And basically that's what happens. Everything collapses to a point, and we get the cosmology that many of you, or perhaps all of you, have heard of, the Big Bang cosmology. So the Big Bang was the start of the universe where everything was really concentrated at a point, including space and time. So let's add this Big Bang cosmology to our list of cosmologies up here on the right, and so that's 1930. Great, so we've done 4,000 years of cosmology, we can move on finally to the biggest problem in physics. And you might be thinking, okay, we've explained all the observational evidence, what other problems could there be? Well, we've had almost 100 years between now and 1930, and there have been a lot of observations since then. So just to cement the cosmology that we're working with in 1930, is we have a universe which is spatially flat. So, I mean, I won't get into too much detail what that means, but basically, it's a universe where space and time are, well, flat. And importantly, we need to know what the energy content of the universe is, right? So the universe is not empty. It's also important to know what the matter content is of the universe, or energy content of the universe is, because as you remember, energy causes the dynamics of space-time. Energy causes curvature, and the universe is basically made up of space-time and energy. So in 1930, we had a universe which was expanding and completely dominated by matter. And that's a type of energy that we're all very familiar with. It's what makes up everything in this room. It's what makes up human beings. So we were very comfortable with our cosmology in 1930. Unfortunately, humans keep looking and keep finding problems. So we move forward 60 years to 1990. And this is when the problems for this idea of the universe started to emerge. So the observations in this case were the observations of galaxies. So in 1990, people were pointing their telescopes into the night sky. They were observing the distribution of galaxies in the universe. And the distribution of galaxies in the universe can tell us a lot about the matter content of the universe. So they took this observation and they compared the theoretical predictions from the cosmology that I mentioned, the matter-dominated expanding universe of George Lemaitre. And what they found, so here you can see basically data, so well, on the vertical axis is called the correlation function, and it basically describes the distribution of galaxies in the universe. On the horizontal axis is basically the angular scale on the sky. Okay? So what we see here, the black points, are our observations. They're the observations of the galaxy distribution as a function of how far away these galaxies are from each other. The lines that you see are the predictions of our cosmological model from 1930. And what we see here is that the lines don't match. There's a problem. Why don't the lines match? So what this suggests, this observation, which was made in 1990 by Maddox et al., it suggested, among other observations, that the energy content of the universe was not completely dominated by matter. In fact, to explain this observation, you would need 30% matter, but 70% of something else to keep the universe flat, which is what we wanted to do for other reasons. And we didn't really know what this other 70% of energy in the universe was at that time. So moving forward 8 years, people were making other observations, and in particular, one observation that won the Nobel Prize years later was the observation of supernovae. So supernovae are exploding stars that we understand extremely well because of nuclear physics. And using these supernovae, what we can do is we can take Hubble's relationship. So if you remember, Hubble's relationship was a relationship between distance and speed. We can take that relationship to much, much, much further distances. So to give you an idea, Hubble's observations took us about 1 million light years away. So they were looking at galaxies roughly 1 million light years away. Supernova measurements can take us to distances of 2 billion light years away. So much, much further. And again, we see the same thing. So we have data points, which is, I mean, these are not really distance and velocity, but they are related to distance and velocity. We have data, which are the green and red dots, and we have our theoretical predictions for that data. And the red line that you see, which is diverging from the data points, is the cosmological model of the 1930s. So things aren't working, but something is working. So we see the blue line is going right through the data points. And what is this blue line? This blue line is the biggest problem in physics. So the blue line says that yes, there's 30% matter in the universe, but what's the other 70% of the energy? That is a form of energy which is causing space-time to expand faster and faster as time goes on. So it causes an accelerated expansion of space. And so you needed this really weird energy component to explain these supernova measurements. And that, yeah, like I said, won the supernova teams the Nobel Prize. Fast forward to 2018, we have another really important cosmological observation, which is called the cosmic microwave background. And so this observation, what you see here, is the light emitted from about 300,000 years after the Big Bang. And what you see is it's not uniform. There are small fluctuations. And you can map the distribution of these fluctuations very simply in a plot very similar to the plot you see at the top middle, so the galaxy distribution, we can do the same thing for the fluctuations in the temperature of light from the early universe. And what we get is an exquisite, this is the best observation in cosmology. I mean, there are no observations which are as precise as this. And also the match of our prediction to the data points is incredible. So I really want to emphasize, if you look at the data points towards the right of this plot, the degree of uncertainty on those data points is tiny. And our theoretical prediction goes right through the data points. And what is our theoretical prediction? Well, it's the same cosmology from the 1930s. We took off 70% matter, we kept dark energy, and we've just refined the numbers a bit. So a model with roughly 69.2% of this dark energy and roughly 30.08% of matter can explain these little fluctuations in light temperature from the early universe. And so this is probably the most defining piece of evidence for our current cosmological model, which is called lambda CDM. And so lambda stands for dark energy. We call it lambda in the equations. And CDM just stands for cold dark matter, so it's matter. Okay. So what is dark energy? So what I told you is that it causes space to expand at an accelerated rate. Do we know anything else about dark energy? Well, so we know it's dark. And what does that mean? It basically means it doesn't interact with light, so we can't observe it directly. We can only observe its effects through gravity, through gravitational effects, or its effects on space-time. We know that it has a constant energy value everywhere. So its value of energy in this room is roughly the same as its energy value in between here and the sun, or between our galaxy and Andromeda. It's the same everywhere at every point in space. Which is unlike matter, right? So Earth is very, very clustered. We have a lot of matter on Earth, but no matter between here and the sun. So it's very different in that sense. And it causes space to expand faster and faster. So it exerts this negative pressure or tension on space-time. Okay. So again, we'll put our scientist caps on and construct our probabilities for a model with no dark energy or a model with dark energy. And hopefully you've been convinced that dark energy is actually something in our universe that we need to explain. Okay. Just a little emphasis there. Everything's dark. Okay, so let's maybe go through a quick recap before moving on to the last part of the talk. So we started off with a bunch of cosmologies or cosmogonies that people had thought up, 4,000, 5,000 years ago, starting with things like this dual idea of living pyramid and the pyramid of the dead. We moved on to the static Einstein universe, where space-time is flat and matter causes space-time to curve. And then we had George and his expanding space-time model, where we started at a point, the Big Bang cosmology, and space is expanding as time progresses. And then we found out that, okay, not everything can be matter. We need some other weird energy components to explain all the observations that we're seeing. And finally, we've arrived at our understanding of the universe today, which is that we need something which behaves very, very strangely. It behaves like something that we're not familiar with here on Earth. It causes space and time to expand rather than to contract as gravity or matter does. So this dark energy. Okay, so this moves us to the last part of the talk, where I'll talk to you about really what's going on today in terms of cosmology and things that are going on at the Royal Observatory too. So In the background here, I'm showing a telescope, which is called the Dark Energy Spectroscopic Instrument. And it's one of many missions that have been commissioned last decade, and that are beginning observations this decade. And so let's take a moment to emphasize how powerful these new missions are. So if we go back to 1990, when we look at this observation used roughly 2 million, I believe 2 million galaxies to construct this correlation function. So those dots were constructed using 2 million galaxies. That's not a lot of galaxies. There are many, many more galaxies in the universe. And to give you an idea of how small a sample of the galaxies that is, it's like if I looked at Glasgow, well, if I didn't look at Glasgow, if I saw the film Braveheart, and I took that as an example of what all Scottish people look like, that is basically the equivalent of using that measurement to explain what the universe looks like, based on galaxies alone. And so I have a picture of Brave. Yeah, there it is. So it's a very, very small sample, and we can't really base too much off 2 million galaxies. We need to observe more. So coming back to these missions, how many galaxies are they going to be observing relative to 2 million that we observed back in the 90s? So this decade, like I said, we have the Dark Energy Spectroscopic Instrument, but we also have the Euclid satellite, which I'm involved with, and it got launched in July. It's another galaxy observing mission, currently undergoing data collection. And these missions together are going to observe roughly 1,000 to 10,000 times more galaxies than the first galaxy missions back in the early 90s. So that's roughly, I think it was 20 billion galaxies one of these surveys will measure, compared to 2 million of the 1990s. So that's a lot. That's a much, much better sample size to base any conclusions on. And to give you an idea of how big this telescope is, Euclid, that's my boss next to the Euclid satellite when it was still on Earth. I don't know if she was trying to sabotage the mission, but it's pretty big. So it's about I don't know, 10, 15 meters, 20 meters in height. And it got launched on a SpaceX rocket, like I said, in July. Okay. So I called this part of the talk Galaxies and Machines. So we've talked about galaxies. What do machines have to say in this part? So when I say machines, I really mean machine learning. So what I'm doing a lot now is I'm leveraging the power of tools, artificial intelligence tools, to analyze observations of galaxies in our universe to tell us more about cosmology. But in particular, to tell us more about the biggest problem in physics, which I told you about, which is this dark energy component that we don't really know too much about. So how am I doing this? So here is a little game I put in a few talks of mine. And at this point in the talk, I asked the audience, okay, one of these pictures is a face, and one of these pictures is 3 rashers of bacon. And I asked them, okay, who thinks this is the bacon? Usually no one raises their hand, so very good. I do the same here, no one raises their hand, but it's clear that, well, maybe to some of you, that's the face, and this is bacon. So what's going on here? What's going on here is image recognition, which we can all do with faces and bacon. We're very good at that. But what about faces of the galaxy distribution? So I'm going to show you 2 more pictures. So this is again a measure of the galaxy distribution, the correlation function. You had seen one coming from the observations of 1990. Now I'm giving you 2 more. These are predictions, okay? They're not observations. These are predictions of a theoretical model, a cosmological model. One of them uses Einstein's theory of general relativity to make the prediction. One of them uses a different theory of gravity, a modified gravity theory, to make the prediction. And I would ask the audience, okay, tell me which one is general relativity and which one is modified gravity. We won't go through that. I'll just show you. That one's modified gravity, and this one is Einstein's gravity. They look exactly the same to our eyes. But to machines, they don't. So machines are extremely good at doing recognition problems like this. So what we're trying to do now in Edinburgh, is, well, we've already constructed an algorithm, is we have an algorithm which has been trained on predictions like this. And so when we actually get the observations from the telescopes that I mentioned, we can feed it to this algorithm and it can tell us, is everything consistent with Einstein's theory? Or is there something else going on? This does not look like a prediction that Einstein's theory would make. Do we need to modify gravity to explain these observations? Okay. How else are we using machines? So to explain that, I'll need to go through something a bit more complicated than what we've seen so far, but not too much. So here, as we've seen throughout the talk, we have constructed probabilities, and so far you've only seen one-dimensional probability distributions. So we had two hypotheses. We said one is more probable than the other. Here we have a two-dimensional probability distribution, and basically it's mapping out the probability of the universe containing dark energy and dark matter, and to what percent. Okay? So as you see here, I've plotted a probability distribution based on the observations that I showed you earlier, which shows that we need roughly 70% dark energy and about 30% matter to explain the observations, with some probability spread. We can't rule out, a universe with zero dark energy, but it's extremely unlikely. So this is a two-dimensional probability distribution, and if you look into scientific papers or cosmology papers, you will see plots like this everywhere. They're basically probability distributions of where we think we are in terms of cosmological model. What's the problem here? So the problem is that we are trying to use all the data from these missions, which includes many, many physical effects, such as effects from supermassive black holes at the center of galaxies, which are ejecting matter out of the galaxy and are causing all sorts of strange effects on the correlation function, which we don't want. We just want to extract all the cosmological information. We don't care about extra gas being expelled from a galaxy. But we need to account for these things in our analyses. And so what does that mean? That means we have to put into our model extra knobs that we can turn, which will account for these extra physical effects, astrophysical effects, different particle effects. We need to include these knobs, otherwise we're going to get the wrong probability distribution for our cosmology at the end. And so you'll ask, okay, so how many effects are there? There are a lot. So here we have a two-dimensional probability distribution. We have two knobs. The knob is how much dark matter or how much matter, and the other knob is how much dark energy. In a real analysis, which I'll show you soon, we have about 30 to 40 knobs that we can tune. So that's the probability space that modern analyses have to explore. Every single box you see here is just a two-dimensional slice of this 30-dimensional probability distribution. And each of these purple contours that you're seeing are telling us where in that space we're most likely. So if we look all the way down here, you can't see it, but down here we have the percentage of matter, which is what we want. It's this omega n there. And so we really want to pin things like that down. We don't really care about all these other knobs that we can tune, but we need to tune them and let the data tell us where they lie. Otherwise, we're going to get the wrong probability for example, the matter content. So how do you do this? How do you tune all these knobs based on the data? It's very hard. And that's why we leverage things like machine learning, artificial intelligence, to speed up our predictions from our cosmological model, to probe this incredibly big probability space, or parameter space. Okay. All right, so I have 2 more slides. Hopefully, I don't know how I am on time.
You're okay. Right,
Okay, great. Okay. So 2 or 3 more slides and we're done. I know the previous slide was a lot. It's a lot for me too, and I hate looking at those things. Unfortunately, I look at them all day. So, what is dark energy? What can I do this? And I included this because there were some recent results which might be of interest to many people here. So, the new results tell us a bit more about dark energy, and we'll come to the new results shortly. But which of these things does it tell us more about? And it really tells us more about this thing. So there were some results from the dark energy spectroscopic instrument released a couple of weeks ago, which suggest that dark energy is not the same everywhere, but to be more precise, every time. So we still think that it's the same everywhere in space, but there are some results now that suggest it has evolved as the universe has evolved. And so I'll show you those results now. So the Dark Energy Spectroscopic Instrument, it started taking data, I believe, in 2021, and it had its first paper release recently, like I said. And so here we have, again, probability distributions. We've gone back to 2-dimensional. And so DESI stands for Dark Energy Spectroscopic Instrument. You see 3 probability distributions there, where we have the DESI observations of galaxies combined with the cosmic microwave background combined with supernovae. So the last 3 things you see on the right, Pantheon plus, Union 3, DESI 5, those are all supernova data. And then you'll ask, what are these, what is the vertical axis and what is the horizontal axis here? So what probability distribution is this? Well, so this is the probability distribution of the dynamics of dark energy. So on the vertical axis, we have how fast has dark energy been evolving over time. And on the horizontal axis, we have dark energies change over time. So one is acceleration, one is speed. And a constant dark energy is what we thought dark energy was up until recently, is there. And you see it lies just outside of the majority of our probability distribution. So, yeah, maybe I'm showing this to just highlight how things are changing quite quickly this decade in terms of our understanding of this dark energy component. These results suggest that it isn't constant, and the fact that it's constant has been something that's been accepted for 25 years now. So that's slowly changing, and this is only the very first of 3 or 4 major surveys to be taking data. This is one of the first results that they've been producing, that they've produced. Okay, so hopefully that's exciting to some of you. It's quite exciting to me to think that over the next 10 years we're going to learn a lot more about this weird energy component that is dominating our cosmological model. So just to say, the future might be darkening, because dark energy is working, but actually, in terms of human knowledge, things are getting a bit brighter. And I'd just like to show some of the people who are working on these things with me. You might remember the person in the middle, the person trying to sabotage the Euclid mission. That's Alkista. She's a professor at the Royal Observatory. And Linus and Maria are both PhD students, and they have done the majority of work which I've showed you about these 30-dimensional parameter spaces. But Linus is also working on this image recognition for correlation functions or galaxy distributions. And there are many people at the observatory who are part of all these missions. It's a hub for the science part of all these missions. So if you're ever looking for speakers, you should definitely contact people. There are a lot better speakers than me. In particular, Linus and Maria are fantastic speakers, so if you're ever looking for speakers, you should definitely contact them. And that's all I have to say. Thanks for listening.
Thanks very much. That was fascinating. So, have you got any questions?
I was reading today that the new prediction is that the dark matter is made of tachyons.
Oh, I haven't heard that.
Yes, that's what I read that.
Yeah.
It's a published paper in America,
Okay.
and it predicts a lot, it maps a lot of the things we've observed. But they can't find tachyons, they think they go faster than light,
Yeah.
and so they can't find them. But there's a model that they fit into, and the energy characteristics match it. This is out today, I think I haven't seen it.
Okay, I haven't checked the archive today, so.
Tachyons are the future.
Yeah, but the thing with tachyons is that it violates.
Does it violates all the
Yeah,
Einstein's theories? Yeah.
and yeah, so maybe it introduces more problems than it solves.
It does, first of all, yes.
Yeah. Just so everyone knows, tachyons are particles that move faster than the speed of light, which is a problem in many ways. But it solves Darkening.
It's just it's a published paper. It's not been reviewed yet, though.
Yeah, people work on tachyons. I know people who work on tachyons, so it's not.
It's an American paper.
Yeah.
Yeah, got the black there. Right.
You talk about reality, and reality seems to change as time goes on. Everybody knew their reality was right.
Everyone?
Everyone at that time knew their
Yes.
reality. What do you think the next reality is going to be? In fact, what is reality?
Well, that's a good question. I think, okay, so I have some thoughts on that. I think the first thought is we basically recycle ideas a lot. So if we just look at the conceptual level, there are many concepts from the cosmogonies I showed you that are being reused. So like this idea of, well, we had Robert Koseke saying that there was a Big Bang type of thing happening in 1200 AD. So there's that idea. The multiverse idea is very, very much still alive, and that was being proposed by Anaximander in ancient Greece. So conceptually, reality I don't think has changed too much, and there's still a lot of room for interpretation of the cosmological model. But you're right, it is narrowing down, and I think the trend is that we are slowly reducing the center of things. So if I can explain a bit more. So we had a geocentric universe, we moved on to heliocentric. Now we have a homogeneous and isotropic universe where we're not the center of anything and nothing is the center of anything. And so maybe that's the direction where we're heading, where there's no center, you know. Yeah, I don't know what to say, honestly. Like, I don't know. It just feels like we're removing the centers somehow. And that seems to be a trend that I've noticed. And if I can say one more thing, I have a friend who's a string theorist who's working on something which is quite interesting, which is that space and time are just emergent quantities coming from a quantum fluctuation or quantum fields. I don't know how much you know about quantum mechanics, I don't know if I said too many technical things there, but it basically says that nothing is real, everything is just something that has come out of something else, and it's a bit like an illusion, I want to say. I don't want to say illusion, but yeah. Anyway, that was a jumble of ideas. I'm sorry if I, yeah. Hard question.
Yeah.
What is your educated guess on the implication of the fact that dark matter energy is not constant?
What do I think about those results?
Yes.
I wouldn't take them too seriously.
Okay.
I pumped it up a lot for the talk. It's exciting. I mean, I believe that they got the result that they got. But what I showed the probability distribution, and that's what we call the 2 sigma bound. So that's basically 95% of the probability, the full probability distribution, which needs to add up to 100%, is in that circle you saw, or ellipse. That doesn't mean that the constant is ruled out. It just means that it's slightly unlikely to be true. If we see, with more data, these ellipses will shrink. If we start seeing that they shrink and the constant value gets further and further away from the majority of the probability distribution, then I would completely trust the data. It's not constant, it's something else.
So it's too early, basically.
It's too early, yeah. Wait 1 or 2 years, I would say. And then
Perhaps right at the very back of the room.
Why do we
Yeah,
assume,
actually,
why do we assume that space-time is flat in the first place?
why do we assume that it's flat? That's a good question. So it can be one of 3 things, basically. So it can be closed, and so in a closed universe it's a bit like a sphere. It can be open, which is like a saddle, yeah, or flat. And flatness is in very good agreement with cosmic microwave background observations, basically. Yeah. So observations have told us that it should be roughly flat.
yeah, one more.
I have 3 questions. The first one is about the modified and general relativity.
Yeah.
There's a modified gravity for dark matter. Is there one for dark energy?
Yes, yes.
And the other question is, if the finding of the dark energy rate is not constant, then how does it change? Does it change like linear, non-linear?
Good. Yeah.
And the third and last question was about the shape of the universe.
Yeah.
Why, like, I know the 3 main categories, but they're like, why not like more like topologically, more, I don't know, spotted universe, donut universe, anything like that?
Like really weird. Okay. So let's go systematically. Okay, so modified gravity, that explains dark energy. So I'll rephrase that question. We have accelerating space. We think dark energy is causing that. Can changing gravity cause that? And yes is the answer. There aren't any very good theories which do that at the moment, but people have tried a lot. And there were good theories, but more observations have sort of told us that they're not very likely to be true. But people are working on that. That's a big area of research at the moment, to try and find a theory which can explain the acceleration without dark energy. So yes. The second question was related to this plot. Yeah. So what this plot is basically telling us is that, I'll just give you the summary. It's slowing down. So dark energy, the rate of change of dark energy is getting slower as time passes. So this is, I don't know if you're familiar with the big rip. There are 2 options, right? So there's, in this case, there's W0. So dark energies change with time. If that is less than -1, so on the other side of the axis, which I'm not showing, that means in a finite amount of time, the acceleration of the universe will be infinite. So that's bad. That means everything will be pulled apart in a finite amount of time, including the particles that make up your body. We're on the other side, so that means it's slowing down. So that's to answer your question. And the third one is, yes, I think there are some theories which consider like very, very strange topological universes, but I would say not many people work on them. But to rest on that a second, when I say that the universe is flat, I mean at very, very large scales. Of course the universe is not flat on Earth. Earth is causing space-time to curve, that's for sure. But at very large scales, it's roughly flat. So, yes. But yeah, I think that's...
So flat Earth works after all.
Yeah, flat universe works. Yeah, they almost got it right. They just, one word.
In your slide prior to this, you
Yeah.
had all the different kind of laws and variables and factors, and you said one of them was like supernovae and things like that.
Yeah.
What are some of the other factors that you also look at as well? Are some of them observable?
Oh, that's,
And
yeah.
are some of them also based in more quantum physics?
No, nothing's based in quantum physics here. This is the one you want.
Yeah.
Yeah, the traumatic plot. Okay, so yeah, so some of them are things like supermassive black holes ejecting gas. I don't know about. Some of them are things like neutrinos. Yeah, so the mass of the neutrino particle is one of them. That also affects the structure, the large structure of the universe, or the matter distribution. We also have uncertainties. These are the uncertainty in the, we call it redshift, but it's basically the distance away those galaxies are. So there's uncertainties there that we need to change. To explain some of the other ones, so this is actually for a modified gravity theory. So this isn't Einstein's theory, so we have an additional knob which tells you how modified the theory is, for example. And maybe I can explain one more. One more is, again, another type of systematic effect, which is basically the shapes of galaxies prior to their light being bent by matter between us and that galaxy. So what were their intrinsic shapes like before the light was bent? So we don't know that. So that's another one. So you have all sorts of things here. Yeah.
Can I ask a much simpler question?
Yeah.
Why is it, how is it that the round Earth model can explain why you can fly from Japan to the USA and the flat Earth model can't?
Well, I guess you could fly to Japan to the USA, but then could you keep going and go back to the USA in the flat Earth model?
Right, so you mean you can't go off there as you come back?
Yeah, I don't think that. Yeah. I mean, you could, and I guess if there was a flat Earth, people would come back and tell you, oh yeah, it's flat.
Yeah.
But so far, no one's told me,
Okay.
yeah, that's the point. Yeah. But yeah, good. I had to think a second about that.
Because you could always fly back away.
You could. So then, to go back to the anecdote I told you about my cousin calling me, I said, well, then how will you explain international flights? And she's like, oh, but the pilots could be in on it. And so you could always have situations, right, like a really complex model where everyone's in on it except you and a few other people. But you construct your probability.
Yeah, thank you. I'm enjoying being completely bamboozled. But the point that was asked in your explanation about how at a huge scale the universe is flat. Is this from the sort of assumed perspective outside the universe, looking at it, that you're describing it as being flat, or just from the data? I'm confused. Is it flat as in there's no ripples, or are things expanding at different rates? Does that fluctuation count?
Okay.
Curious.
So, first question. I would always avoid thinking about observing the universe from outside. Everything that we know exists is inside. So no. But to get around that, I would give you a very unsatisfactory answer. And you would just measure the angles of a triangle. And those should add up to 180 degrees if you have a very big triangle at large scales. In a closed universe, for example, so you imagine a triangle on a sphere, the angles would be larger than 180 degrees. So it's very unsatisfactory. I'll think about it and maybe I'll have a more satisfactory answer for you. What was the second question?
The uniformity of it, its flatness.
No, so there are ripples. People have observed gravitational waves, which are caused by really massive objects moving in space-time, and they cause these ripples of they cause ripples of space-time. And so that just means you can imagine if you had an observer on that ripple, or somewhere fixed and the ripple moves past him, the time that you would see him observing would change as the ripple passes. So just the measurements would change. So you have things like that. You have, like I said earlier, you have really dense objects causing really big deformities in this flat space-time, like black holes, which cause infinite curvature. So it's not flat everywhere. It's got holes and it's got ripples, but on average, it's flat. Or at large scales.
How did the observation of supernova help with measuring dark energy in that second last one here?
Let's take a look at that. Yeah, okay. So it helped because we could map, so you remember Hubble's relationship? We could extend that to much, much larger distances. So we could see how the universe was changing very far in the past, much further in the past. And so what we see is that the change in the past was less, so the expansion of space was less in the past than it is today. And that must mean that there's an acceleration or an increase in the rate of expansion. Yeah, that's basically it.
I'm going to raise a question, if I may, that we mentioned earlier on. How does all of this relate to the other big problem at the moment, and that is resolving the Hubble tension?
It doesn't. Nothing I've talked about really says anything about the Hubble tension.
But it must have some relevance to this, does it not?
Yeah, so the Hubble tension, to let people know, actually I can show you the Hubble tension. Well, this slide does well. So the Hubble tension is a big problem as well in cosmology, not as big as dark energy. And it's basically an inconsistency in the predictions of the model for two different data sets. So it's the CMB and supernovae. And both of these observations have a prediction for the rate of expansion today. How fast is space in the universe expanding today? The CMB says it's expanding at 67 in some units, in some expansion units. And supernova says it's expanding at 73. The units aren't important. And this is what we call the Hubble tension, because it's a tension between these two data sets, and it's becoming quite statistically significant. So that means the probability, if we come back to this idea, the probability distribution for it being 73, if you look at just supernova, is very tight, around 73. If you look at just the cosmic microwave background, it's very tight, around 67. And so, yes, I mean, nothing I've talked about really says anything about this, but what this hints to is that the model that we're using, the cosmological model of the expanding universe with dark energy and dark matter, is breaking. And it's breaking because our observations are getting finer, and of course, if you refine your observations, then your model will break at some point.
Yeah. It's getting into the public consciousness now, because purely as it happens, as I was parking the car this evening here in Glasgow, I was listening to Radio 4.
Yeah.
There's a science programme on at 4:30 to 5 o'clock. And on there, they were talking about the Hubble tension and the fact that this week there's been a meeting at the Royal Astronomical Society.
Yes, there was.
Taken about, very prominent and eminent cosmologists discussing this. And it's now to the point where it's now considered to be so important that Joe Public ought to know about it. And they were talking about Hubble tension on that very programme. I'm thinking, if it's got that far, it is getting to the point where all of this is now there's a big question mark there as to whether it's actually all correct or not. And it worries me for the reasons we talked about earlier, but that's separate. But it's kind of trying to mean, could it be that we're making assumptions about that supernovas are all more or less of a certain class, are all the same? Could it be? I don't know about, not necessarily involving separate variables here, but we're making basic assumptions about things like supernovas, whether they're all of a certain type, type 2, type 1, and all the rest of it. And that's the basis of part of this. Maybe we're making similar mistakes, or it's not quite as uniform as we think with regard to the CMB. I don't know. I'm just layman, but it does seem that there's an air of disquiet now sort of taking hold within, the cosmological experts. I don't know.
No, so it's a huge topic, like I said. You're right. I think it's good that you mentioned the potential problems with the supernova measurements. So, like I said, that that graph you see in the middle is really plotting the speed, which is the redshift, and on the vertical axis is the distance. And then you can ask, how the hell do you get the distance of these objects? How do you measure them? And so the way supernova teams measure these things is they look at something which is close by, and they can measure the distance to that thing close by just by the motion of the Earth around the Sun, for example, things like parallax, if you're familiar with the parallax method. But you can measure it through motions, so it's a very direct way of measuring it. And then the game you play when you want to go further is you try to standardize things. So you look at things that oscillate, for example, like Cepheid variables. They're stars which have an oscillation in their luminosity, I believe, which is very regular. And based on that oscillation, you can also infer a distance. And then, once you've calibrated the distance between supernovae, between us and the Cepheid, so one of these variable stars, then you can move further by using that calibrated distance to further Cepheids. And then you find a galaxy where there's both a Cepheid and a supernovae. You calibrate that distance, and then you go further. But if you make any mistake in any of these calibration steps, then you're going to have problems in the inference at the end. The probability that you infer at the end is probably going to be wrong, depending on how badly you calibrate. So yes, that's something that many people throw around. They say that probably one of these steps has been, done wrongly, or we can't trust it. Are supernovae, is the light from supernovae the same if you go back in time? I mean, we don't know. Maybe this is the assumption. So there are assumptions that go in there. There are simple ways to address the Hubble tension, I think, and there are complicated ways. This is a simple way. We made a mistake, so that's easy. But it's really good food for theoretical physicists who like to come up with all sorts of crazy ideas of why there is an observation. So there's also things like early dark energy. These are real names. Early dark energy or early new dark energy. Yeah, it's a bit of a zoo when you look at the types of theories. Yeah.
Dr. Bose, you're now in Edinburgh, man, is that right?
Yes, yeah.
Did you ever meet Professor Higgs, the Higgs boson?
No, I
Did you
didn't.
ever?
No, I never met him.
Anyone in your department?
I'm sure John, do you know John Peacock?
How did they feel when they first announced this new particle, which is equivalent to Olympic swimmers in the dark? They didn't realise they were swimming in water.
Yeah.
So the universe is like an enormous swimming pool with the Higgs boson.
How did it feel for me?
How is that new discovery?
Yeah.
How did that waking up anyone? Any new theories or new ideas about what the universe is, how it's behaving?
So this is jumping a bit.
Particle physics wise.
Yeah, this is particle physics. So I didn't feel too much when they announced that they found it, which sounds a bit sad, I guess, or I don't know. But if they had told me that they understood what the particle for dark matter was, I would be far more excited, for example. Because
for that to be done in pencil and paper,
yeah,
in theory, coming from a guess, a good guess is as good as a good theory.
Yeah.
Famous man once said, Feynman.
You have to keep in mind that everybody in the community was expecting the Higgs boson.
Oh,
we were just not sure on the mass exactly. But
just like
yeah, it was accepted basically way before we found it.
Yeah,
which is not the case with dark matter or dark energy because we don't know what it is.
Yeah, we don't know what it is.
So we have no clue.
And that's like gravitational waves. I mean, I remember going to talks about that in the 70s, and I think they all accepted, that the gravitational waves exist, and it was amazing the day when it came through.
I remember my master's supervisor had gone to him and said, before I started, I'd love to work on gravitational waves. And this was 2008. And he said, don't do gravitational waves. No one's ever going to detect them. Let's do something more realistic, like studying the structure of a neutron star in the presence of modified gravity. Yeah, so here we are.
Okay. Well, this has been absolutely fascinating tonight, and once again, we can thank
Really good questions.
You've got more questions.
Nobody from